Alright, this example is the demonstration of how to compute odds ratio estimate from binary GEE for certain unit increase in IV. So it is also related to interpretation of fitted GEE model. Okay. As we know, in public health, it's very important to get estimate for relative risks. And odds ratio is one of the preferred measure of risk association. So if we have a binary GEE model, it's very nice if we have a direct way to extract the odds ratio estimate and its confidence intervals. And here's how we do it. Okay. So first, let's read in the data set here. So it can tell us there were 1,086 observations and 6 variables. Okay. And second, look through these SAS code for the binary GEE. So proc-GEMO data equal to keratotomy descent. That means we're modeling the probability equal to 1. Okay. And the class statement define 2 categorical variable, patient ID and gender, and this is the parameterization for the gender. We use female as the reference level. And the model statement, the DV is unstable, which is a binary, and then regress on age, diameter, gender, and the visit. Now 4 IVs. Distribution equal to mean and type 3. And now this is the GEE statement, repeated subject to patient ID / we're asking for the working correlation matrix, the model-based standard error estimate, and we use a unstructured correlation structure, and we ask SAS to print out the initial MLE estimate for the first model it fits, assuming independent correlation structure. Now here's the main thing of this video is we use the estimate statement to get 10 years increase in age. We want to get the risk of how does that increase the risk of unstable. Okay, so this is the label, and this is the variable, and this is the value, and /exp. And similarly, we have estimate for 1 millimeter decrease in diameter, and we had a diameter at -1/exp. And we have male versus female gender equal to 1, then exp. And we have 1 year increase in follow-up, so visit, since its increase is the +1 and /exp. So let me bring you to the SAS documentation. This is for the estimate statement. We know the estimate statement, the syntax is you get a label, and you get the effect, that's one of the IVs, and you get the values. So what the value is really define the one row L prime matrix. Okay. So like here, you get the L prime beta, and the exp option, you get the E exponentials of L beta, then and its standard error and its confidence interval. And in the binary logistic GEE, we know when we exponentiate L beta prime, we get the odds ratio. And then this option, the EXP, allows us to get the odds ratio, its confidence interval, standard errors, and it uses the so-called delta method. Okay. So if you are wondering why we can use like 10 years increase in age, because in epidemiology sometimes the disease may take a long time to develop. So if you use 1 year, it may be too slow. Okay, you get a very tiny increase in risk. So if you look at 10 years, then it makes sense. And then these 10 years, though, you need to scale the variable. So why you get age 10 here? Okay, so basically, if we go back here, we're trying to estimate L beta equal to 0. And if beta is age and we use the age 10. So basically, well, we're estimating, say, EXP of 10 beta. Okay, we're getting the odds ratio of this. So now the beta is corresponding to age. Okay, the regression parameter for age. But if you estimate the odds ratio for this, then back to the regression equation, you get the logit of p equal to say beta times age, for example. Of course, you plus other stuff. Okay. So what this is, if you now you're saying I want to estimate about 10 beta, then this is equivalent, say you're at the same time you have to scale age by 10. Okay, so now you're estimating this as the odds ratio. So by doing this, you actually scale the age by 10. So that's 10 years. Okay, so let's run this chunk of SAS code. So we're going to get all the model fit and parameter estimates, and as well as the odds ratio estimate. So these are the odds ratio, this mean estimate, and then you get the confidence limit. Okay, I'm sorry, this is L beta, this is the odds ratio. Let's see, mean estimate, yeah, and then mistake, mean estimate should be the odds ratio and its confidence interval, and this is just the L beta. So this is the n exponentiated. Okay. So this is an example of showing you how to compute the odds ratio and the confidence interval, and especially after scaling a variable such as age.